Okay, now we start conduction. The conduction is the transfer of energy from the more energetic particles of a substance to the adjacent less energetic ones as a result of interactions between the particles. So in conduction, there is a direct interactions between the particles in a given substance. And conduction is generally understood being associated with heat transfer through solids, but that's not correct. Conduction takes place in gases and liquids as well as in the solids. In gases and liquids, conduction is due to the collisions and diffusion of the molecules during their random motion. But in solids, it is due to combination effect of vibration of the molecules in lattice and energy transport by free electrons. There are two mechanisms, as we discussed, in solids for the mechanisms of conduction. Okay, let's consider this wall. The thickness of the wall is delta X, thickness of the wall. Surface area is A. So the surface area is area of the wall. This is the thickness, and A is the area. Width times height. Area is, okay. So the area is width times height. So that is the area, okay. Height is this is your height. Width is into the page, into the screen, okay, normal to the screen. Okay, area is this. Okay, this is the area. Okay, how do I? Okay, now I deleted that. Okay, so this is the area. I hope you understand what the area is. Delta X is the thickness of the wall. So this side of the wall, this surface of the wall is at temperature T1. The other surface of the wall is at a temperature T2. And the heat flows through the thickness. Okay, so the area is normal to the direction of heat transfer. Why heat transfer is from left to the right? Why is it left to the right, but not from right to the left? Why? Why is it like this, not like this? Yes, Gülüz is right. It is from high temperature to the low temperature. This is the high temperature. This is the low temperature. More energy to less energy. Okay, good. You are all correct, but the correct expression is high temperature to low temperature. Not from high energy to low energy or anything else. That's the correct terminology. Okay, so the axis in the direction of the X is the same as direction of the heat transfer. So from high temperature to the low temperature. High to low, this is the direction of heat transfer, and X is in the same direction. The positive X direction, this is 0, positive X direction. Okay, so experimental observations show that the rate of heat transfer is proportional to area, more heat transfer. Temperature difference, the difference between this temperature T1 minus T2, and it is inversely proportional to thickness. Okay, observations say that, and I think you can all relate to that. Then using this observation, we can define conduction heat transfer as Ka T1 minus T2 over delta X. So rate of conduction heat transfer is proportional to area, proportional to temperature difference T1 minus T2. It is proportional to inversely proportional to thickness. That's why it is in the denominator. But different walls have different heat transfer characteristics, right? So we need another property which account for the wall properties, wall material. What is that property? That property is K. What is the name of the K? Name of the K? Anyone? What is K? K is the material property. Because if this is copper, if this is brick, if this is concrete, heat transfer is different, right? Or wood. So to account for this material difference, we have a material property in the equation, which is K. Do you know the name of the K? Do you know the name of the K?
Thermal conductivity.
Exactly. Thank you, Ali. It is thermal conductivity. Yes. It is thermal conductivity. Okay, so K is the thermal conductivity of the material. It's a property of the material related to conduction characteristics. Okay. Okay, so Ka T1 minus T2 over delta X. I write this as minus Ka delta T over delta X. Why I have a minus sign here? Can you tell me with your microphone or in the chat? Why there is a minus here? Anyone? Why there is a minus here? Here there is no minus. Here there is a minus. Why? Okay, no answer. Because of direction, that's correct, but I need more explanation. T2 minus T1. Okay, good. Good. Okay, good. I like your answers. I like your answers. Because delta T is, what is delta T? T2 minus T1, right? Here, normally heat transfer, we write it like this, right? Because we know that T1 is greater than T2, right? Because direction of heat transfer is like this. T1 must be greater than T2. Therefore, here, when you apply this equation, what do you get? You get plus, right? So heat transfer is positive. Heat transfer is a vector quantity, so you need magnitude as well as direction. For that reason, here, there is no minus sign because T1 minus T2 is positive, delta X is positive, A and K is positive. So the result is positive. But here, delta T means T2 minus T1. Delta T means that. So this is minus, another minus, so your result is positive. Okay, this is the practical answer. More theoretical answer is, so we define heat transfer from high temperature to the low temperature, and the positive X direction is defined as same as the positive heat transfer direction. So Q and the X is in the same direction. And delta X is positive, right? Delta X, this distance minus this distance is positive. Delta X is positive, but in the positive X direction, delta T is negative, dt is negative. So to make the heat transfer in the positive X direction as a positive vector quantity, we have to add a minus sign here so that your result for the heat transfer is positive. Okay, so this equation can be written instead of delta T, when delta X goes to 0, what happens to this equation? When delta X goes to 0, delta T becomes dt, delta X becomes dx, right? Differential X, differential T. When delta X goes to 0. When X goes to 0, delta X goes to 0 actually. Q dot conduction is minus Ka dt dx. And this equation is called Fourier's law of heat conduction. Fourier's law of heat conduction. You have to remember and learn this. Fourier's law of heat conduction. Okay. Here is another question for you. What is the unit of area? What is the unit of area here in this equation? The unit for area. The unit for area. Okay, meter square, thank you. The unit for delta x, the unit for delta x. The thickness, good. The unit for temperature difference, T1 minus T2. The unit for temperature difference. The unit for temperature difference. Kelvin or degree Celsius? Kelvin or degree Celsius, which one? Not important, same, it is same. Okay, so it is degree Celsius or Kelvin, both of them are correct because it is the temperature difference. Okay, what is the unit for rate of heat transfer? Q dot rate of conduction heat transfer. Rate of conduction heat transfer. What is the unit for this? The unit for this. The unit for this. Rate of conduction heat transfer. Anyone else? Okay. Rate of heat transfer means amount of heat transfer per unit time. So it is kilojoule per second. What is kilojoule per second? It is kilowatt. Okay. Okay, so now the final question here. What is the unit of thermal conductivity? The unit of thermal conductivity. K. The unit for thermal conductivity. Other people, what are your answers? Other people? Other people? Other people? What is the unit of thermal conductivity? Okay. It's very easy, right? A is meter square, degree Celsius or Kelvin, meter, watt, and what is the result? Watt per meter per Kelvin or watt per meter per degree Celsius. Watt per meter Kelvin or watt per meter degree Celsius, right? Both of them are correct. So these are the units of thermal conductivity. So the thermal conductivity is rate of heat transfer per unit temperature difference per unit thickness. Okay. Okay, so this is the Fourier's law of heat conduction. This equation is very important. We call it Fourier's law of heat conduction. Thermal conductivity K is a measure of the ability of a material to conduct heat. The ability of a material to conduct heat. This is thermal conductivity. For example, here, 30 degrees, 20 degrees, surface temperature, 30, 20, same surface temperature, the same thickness. For copper, thermal conductivity is 401. For silicon, 148. The rate of heat conduction heat transfer here is 4010 watt. Here, the rate of conduction heat transfer through the wall is 1480 watt. So it is the material, right? K, material property, makes the difference. The rate of heat transfer is proportional to thermal conductivity. And this dt dx represent the slope of temperature curve on a TS diagram, on a TX diagram, right? dt dx is the slope. Okay. So why do we have a negative sign here? Okay, let's read this very carefully. Heat is conducted in the direction of decreasing temperature, and the temperature gradient becomes negative. This dt dx becomes negative when temperature decreases with increasing x. X is increasing, T is decreasing. So this temperature gradient becomes negative. Dx is positive, dt is negative. Temperature is decreasing, X is increasing in the positive X direction. The negative sign in the equation ensures that heat transfer in the positive X direction is a positive quantity. Okay, this is what we have already discussed. Okay, so here you can see better how the area is. So this is height, this is width. Area is width times height. I already showed you that. L is, what is L? What is L? L is what here? Thickness. Thank you, guys. It is thickness. L is thickness, like delta X. L is the thickness. Height, width, thickness. Heat transfer is in the thickness direction. Heat transfer is normal to the area, right? Normal to the area. A, the area represents the area normal to the direction of heat transfer. Okay, any question? Are there any questions? Okay. Ali Alkın, Celil Can, Emir Özdemir, Emircan, Ender, Gülis, Hacer. Hacer, what is your last name? Write your full name, Hacer. İbrahim, Ceylan, İlker, Halit, Kürşat, Mert, Muhammed Bager, Murat, Mustafa, Necmi, Oğuzhan, Omar. Omar, what is your last name? What's your full name? Write your full name next time. Önder, Süleyman Enes, Umut who? Umut who? Yunus Emre. Do you guys have any questions? Any questions so far? Okay. No question. Okay. No question. Okay, we will continue. There is no reason to stop. Thermal conductivity, there is more discussion about thermal conductivity here. So what is the unit of thermal conductivity? Again, do you remember the unit of thermal conductivity? The rate of heat transfer through a unit thickness per unit area per unit temperature difference. Okay. The rate of heat transfer through a unit thickness of the material per unit area per unit temperature difference. Okay, what's the unit of thermal conductivity again? Remember? Yes. So when somebody writes on the chat, everybody can see it, right? When somebody writes something on the chat, do you guys all see it? Yes, okay. So you can see other messages. Okay. Good. Okay, the thermal conductivity of a material is a measure of the ability of the material to conduct heat. Some materials conduct it better than the others. Tell me some materials with high thermal conductivity. Tell me some example materials with high thermal conductivity. Tell me. Which materials have high thermal conductivity? Some examples. Some examples. Emir Özdemir, what is your answer to this question? Emir, what's your answer? Emir Özdemir. Metals, good. Aluminum, copper. Good answers. Gold. Okay, these are some of the materials with high thermal conductivity. So give me examples for low thermal conductivity. Some examples for low thermal conductivity. Mert, what is your answer, Mert? Mert. Silicon, plastic. Okay. What is the general name for the material with low thermal conductivity? How do we call them? What is the general name for the material with low thermal conductivities? General name. There are some materials, they have very low thermal conductivities. How do we name them? What is their general name? Anyone? Yes. Thank you, Ali. Good answer, insulator, right? And the materials with high thermal conductivity then called? The materials with high thermal conductivities are called conductors, and the materials with very low thermal conductivities are called insulators. Okay. A high value of thermal conductivity means they are a good heat conductor, and low value means they are a poor heat conductor or insulator. This is an experimental system that can be used to measure the thermal conductivity of a substance. The thermal conductivity of some materials at room temperature: diamond, very high; silver, copper, gold, aluminum, iron, mercury, liquid mercury; glass 0.78, brick 0.72, brick 0.72, water 0.7, human skin 0.37, wood 0.17, glass fiber 0.043. Glass fiber is an insulating material. Air 0.026, urethane, rigid foam 0.026. Okay, so they have the same thermal conductivity. So glass fiber and rigid foam, they are insulating materials. Air has the same thermal conductivity as rigid foam and even less than glass fiber. So let's consider this wall. And you have air here. Or you have foam. So in the case of air, heat transfer 1. In the case of foam, heat transfer 2. Which one is bigger? Q.1 or Q.2? The wall consists of air here consists of foam, in which case there is more heat transfer through the wall. 1 or 2? Air or foam, in which case there is more heat transfer through the wall. Okay, I have some answers. Some people say air, some people say the same. Okay. So temperature here, this side of the wall and this side of the wall, it is the same for the case of air and foam. Okay, the correct answer is this. There is more heat transfer. There is higher rate of heat transfer when it is air than the foam. Why? This is the answer. There is more heat transfer, more rate of heat transfer when the wall is filled air rather than the wall is filled with foam. Why do you think the answer is that? You can use your microphone to answer my question if you want, like Ali did. Any answer? Anyone? They have the same thermal conductivity. Air and foam have the same thermal conductivity. Okay, so this is the answer. This is the answer. There is more heat transfer when the wall is made of air than when the wall is made of foam. But Q dot conduction in the first case is equal to Q dot conduction 2. Did you understand the answer now? Q dot 1 is greater than Q dot 2. Did you understand the answer? Is it clear now? I am not getting any answer. Did you understand or not?
Yes.
Yes.
Anladım.
Who is this?
I
Who's
didn't
this?
understand.
Say your name, then answer my question.
Hocam Hacer ben anladık conduction'da aynı ama radiation ve diğer yöntemlerde aktarım olduğu için daha fazla olur.
I am impressed with your Turkish. Hacer, I am very impressed. Excellent Turkish. Good. Thank you for your answer. But try English next time. Good. Write your name fully also in the system. Okay. So conduction heat transfer is the same. What is the formula for conduction heat transfer here? What is the formula? Write the formula in the chat. Write the formula Q dot 1. What is Q dot conduction 1? What is the formula for this? Write in the chat. Q dot conduction 1. So Q conduction is equal to KA delta T over L. Right? Okay. Okay, correct. Good. Okay, because thermal conductivity is the same, the rate of conduction heat transfer is the same. Any questions? Are there any questions? So in the case of air, we will learn that there is also convection and radiation through the wall because it is a gas. In the case of foam, the only form of heat transfer through the wall is conduction, okay? Therefore, Q dot 1 is greater than Q dot 2. Q dot 1 includes conduction, convection, and radiation, all of them, because air is a gas. There is also convection and radiation. But in the case of foam, there is only conduction. Therefore, we have this answer. I hope Okay. Nasıl güzel siliyor muyum? Tahtada silmekten daha az yorucu değil mi? Hacer is now saying that why do you speak Turkish? You tell me not to speak Turkish. Now you speak Turkish. Hacer, are you saying that? Hacer, are you saying that? I don't think so. You don't say that. Okay. I continue. Okay, thermal conductivities. Here are the range of thermal conductivity of various materials at room temperature. As you can see, these are high thermal conductivity materials, like mostly metals. Here, gases, insulators, liquids have low thermal conductivities. Okay. Okay, let me ask you a question. Let me ask you a question in the chat. So copper have a thermal conductivity of 401 watt per meter Kelvin, and nickel has a thermal conductivity of about 90, let's say 100. And you have an alloy of copper and nickel alloy. What is the thermal conductivity of this alloy? K alloy. What is the thermal conductivity of the alloy? Let's say they are 50%, 50%. So copper, thermal conductivity, nickel, thermal conductivity, and you have their mixture, their alloy, 50%, 50%. What is the thermal conductivity of this alloy? Anyone? You are supposed to make a guess. I put everything in the chat. Do you hear me? I don't get any answer. Okay, 250, 250, something like that. Anyone else? What are your answers? $380. Umut, what is your answer, Umut? Umut, what is your answer? $250. Yunus, what is your answer? Yunus. Okay. This is the wrong answer, of course. Of course, it is the wrong answer, right? Wrong answer. Here is, so here is copper has a thermal conductivity of 401, nickel 91. Constantan is the name of the alloy, which consists of 55% copper and 45% nickel. And what is the thermal conductivity of this constantan? 23. Another alloy is commercial bronze, which is 90% copper, 10% aluminum. What is the thermal conductivity of this commercial bronze? 52. Are you surprised? Are you surprised? Of course, you are surprised, right? I am surprised. Yes, that's why I asked this question. But this is the case. The alloys have very low thermal conductivities, less than the two of the material they are composed of. Usually this is the case. So because of the material structure, the thermal conductivity decreases significantly. Normally, pure crystals and metals have the highest thermal conductivities, and the gases and insulating materials have the lowest. Okay, these are the mechanisms of conduction in gas: molecular collisions, molecular diffusion, liquid, molecular collisions, molecular diffusion. But in solid, lattice vibration and flow of free electrons. In metals, flow of free electrons are more significant, of course. The thermal conductivity normally changes with temperature. For example, here in this table, as the temperature increases for copper, thermal conductivity decreases, decreases, decreases. For aluminum, it is decreases also, right? So as the temperature increases, thermal conductivity of the copper and aluminum decreases. Here you can see different materials, how they behave. For helium, as the temperature increases, thermal conductivity increases. For water, it is first increases, then decreases. For iron, it decreases. Silver, copper, it decreases. So different. For gases, usually, thermal conductivity increases with temperature. For metals, solids, usually, thermal conductivity decreases with temperature. Here we define another material property, which is called thermal diffusivity. Thermal diffusivity. And it is equal to alpha is equal to thermal diffusivity, heat conduction divided by heat storage. K over rho Cp. K is thermal conductivity, rho is density, Cp is specific heat. Okay? K over rho Cp. The unit of K is watt per meter degree Celsius, rho is kilogram per meter cube, Cp is kilojoule per kilogram degree Celsius. If you do your mathematics, the thermal diffusivity has the unit of meter square per second. So thermal diffusivity is proportional to the thermal conductivity, inversely proportional to density and specific heat. A material that has a high thermal conductivity or low heat capacity will have large thermal diffusivity. High thermal conductivity, low heat capacity. Okay, so rho Cp is the heat capacity. Heat capacity. And a small value of thermal diffusivity means heat is mostly absorbed and small amount is conducted. Why do we define alpha, K over rho Cp? Because we can use K, rho, and Cp separately, right? The reason is that in some heat transfer equations, we see this ratio often. K over rho Cp comes to us. So we don't want to deal with them separately. We want to name them with thermal diffusivity and use it in our equations. In our equations. Okay. So here in this table, the thermal diffusivities of some materials at room temperature are given. Thermal diffusivities of some materials at room temperature. Okay. As you can see, the metals have high thermal diffusivities, and insulating materials and water have low thermal diffusivities. High values, low values, as expected, because it is proportional to K, thermal conductivity.